Hi everyone, welcome back. So today we are on lecture 10 in the series, and we will discuss patch antennas or microstrip antennas. So I'll just call them patch. We'll also at the end discuss a few techniques associated with general antennas, but in the context of patch antennas. Okay, so the reason I want to focus on patch antennas is just because they've become very popular and they're probably the most popular kind of class of antennas that are designed today. Especially for PCBs and chip design and things like that. We're not going to do some of those slightly older kind of antennas in this class, like Yagi Uda or helical antennas and so on. They're not as popular anymore, especially on the research side of things, they're not really done as much. So we'll focus more on these kind of planar microstrip antennas. Okay, so this is also called microstrip antenna sometimes because it looks like a microstrip line, right? Okay. So what does it look like? And we won't be very rigorous in this class and the next class, just because I want to focus more on design rather than equations. We give you intuition because today pretty much everyone has access to some kind of CAD tool like HFSS. We don't need to know analytical derivations to design a patch. You rather just want to design it and use your intuition to kind of make it work, right? So we'll develop more of the intuitive side of things. Okay, so we have a ground plane, which was in black, and then I have a rectangular patch, like that. Okay, and that's essentially it. So typically the ground plane is fairly large, but we'll see actually that the ground plane has quite an impact on the radiation pattern itself. So the side view looks something like this. You have the ground and patch, right? So maybe I can make it a little bit longer. You can label this. So I'll label this dimension as L and this dimension as W for the length and width. So here I'm really looking at L, okay? So I should say that, let me actually, let's label it here. So this is L, okay? All right, so if you look at the currents on the patch, let's say the patch can be polarized in two different directions. You can have currents flowing this way. So that would be, in this case, V polarized because they are sort of vertical. Or you can have currents flowing this way. So this would be H polarized. Okay. So just, without loss of generality, we'll just deal with the V polarized case. So if current is flowing this way on the patch, right? So keep in mind that this current is not on the top surface of the patch, but rather the bottom surface. So the current really flows on this side. And we'll see because of the feed technique, when you come in with a microstrip line from the left, the fields are mostly confined underneath. Even for the patch, we'll see the fields are mostly confined underneath. So what we're drawing here is the current on the bottom surface. Okay. All right. So we know that, so I'm just going to erase this to make some space. So we know that, if I have, this is my patch metal, we know that current has to be zero at this point and this point, right, from the boundary condition. You can't have a current flowing into air. So if it's a half wavelength patch or approximately half wavelength patch, then the current has to be maximum in the middle and zero on the ends. So sinusoid like that. Okay, and if you think of this as a transmission line, since the current is zero at the ends and maximum in the middle, the voltage should be the other way around. So the voltage would be like that. Let's see, you have maximum voltage at the ends where you have an open circuit and you have zero voltage in the middle. Okay, so we can draw the fields. What do the fields look like? Maybe I choose, let's choose orange for the field. Okay, so the electric field, of course, is zero here, right, because the voltage is zero. And it's sort of maximum at the ends, right? So it slowly grows. So I'll just draw like weaker line, then and it becomes strong at the ends. And then there is some fringing field like that, goes out that way. And the other side is flipped. Right, so you have like that. And then this is strong. And then you have like that, right? That's what the voltage electric field looks like. So this is the E field. This is the voltage. And this is the current. Okay. Okay, and if I plot the impedance, so plot the impedance as a function of L, impedance. So here I'm just plotting the real part. So let me actually write that out. So plot the real part of the impedance. Then at this point, voltage is zero and current is maximum, which means the impedance is zero. And at this point, current is zero and voltage is maximum, which means the impedance is infinity. Right? So it looks something like this. Okay? It's like a tangent function, right? I guess strictly speaking, it should be like this. Maybe let's use that. Hesitate to do it like that. The impedance is not negative. So let's keep it like this. Okay. All right. So which means that at some point there is a 50 ohm, right? So at some point you have 50 ohm impedance. So that point we want to match to with a transmission line. Okay. So let's just say that point is somewhere here. So what I can do is I connect a transmission line like that, or I can put a port here and excite it at that point, right? So finding that point, I would say the best way is to design your patch, do the layout of your patch, put a port, and then sweep the location in L from different points from the center to the end. And at one location, you'll see that it's matched at the frequency you care about. And that would be the location. So that's the easiest way. All right, so the picture on the left, somewhere in the middle. Right, so we want to put it exactly in the middle for symmetry purposes. And we'll see why that's the case. But okay, so you have a port in this case, right? So that's kind of how a typical patch looks like. Okay, so I just want to say that this is a port. Okay, we'll see what kind of feed options we can use, but for now that's a port. Okay, all right. So there are many ways to model a patch, to analyze a patch. So I think the simplest way is just to give you some intuition as to what that looks like. So we have a current on this surface and we have another current on this surface. And they are usually in the opposite direction. So the patch itself, the current on the patch itself doesn't really radiate, right? There's actually very weak currents on the top surface. You don't see much current on the top surface. You can plot it in HFSS and see that. So if you look on this side, you'll only see some current on the sides here. And that's because the H field goes around, H field kind of goes around just like this. Right, so you have some edge current on the top surface, but there's almost no current in the middle. Whereas on the bottom surface, you'll have pretty strong current everywhere. Yeah, and of course, the current decays on this edge and this edge. Okay, so these currents don't really radiate because they kind of cancel each other out, similar to a transmission line. But it is really the current that's on the ground plane that's out here that radiates. So there's a current coming in like this. There's one section here, one section here. Really, these currents that radiate. Okay, so one way to model that is to say that, okay, those currents are associated with these fringing fields. So it's really the fringing fields that radiate, right? And if you look at the fringing field, on this surface, it's pointed this way, the top surface. So if I just take the top surface and I want to find the equivalent currents on that surface, we said that there is no electric current on this surface. You can associate an equivalent magnetic current uh, on these two surfaces, or you can even, which is essentially like saying that you have this electric field that's this way, right, coming from the fringing component, and that's the one that radiates. So if you look at it from above, what does it look like? And so I'm just going to erase this as well. So those fields look like this, electric fields. Right, you have one there and one down here, right? So this should remind you of a slot, right? A slot also has electric fields that are like that. So really, you can model this patch as two slot antennas that are separated by around lambda over 2. And we looked at slot in the last class. Right, so this is one slot, and this is the other slot. Okay. So we can so you can say, okay, it's either radiating as two slots, and that's one way to look at it. And that's in some sense the most intuitive model, right? So this is your electric field. And these slots are separated by approximately lambda over 2. Okay. Okay. To actually understand a little bit more deeply, what we can do is we can develop an equivalent circuit model for the patch. So I'll redraw the patch here. We have our top surface. Do that again. Top surface. That we have a bottom surface down here. It's like that. And I had my port out here. Right? So now I have some fringing field, which I can represent as a capacitance. Like that, right? And there is also radiation resistance. I'll call this RR1 and C fringe CF, right? Because some of the radiation goes into the far field. And that you can model as a resistor, right? So the same thing on the left, another RR1. We have a fringe capacitance, right? And I can model this section as a transmission line, and this section is another transmission line. Right? So now this is going to be greater than lambda over 4, and this is less than lambda over 4. And because the total length is lambda over 2, and the feed is a little bit offset from the center. Right? So, roughly speaking, if I have capacitive load and I have a line that's greater than lambda over 4, then most likely it could end up as an inductor, right? As an inductive load. Of course, it matters what the capacitance is and where you are on the Smith chart, but I'm just speaking roughly. Okay. Okay, so which means that from the point of view of this port, it looks like you have some kind of LC, LR on the left, and you have on the right a CR load. And of course, you could say that, okay, what if I'm at a location on the Smith chart where this becomes a capacitance? If that becomes a capacitance, then this should become an inductance. Okay, because these fringing fields we're assuming are the same. Right, so if I'm on the Smith chart and I'm on the bottom side, now I go greater than lambda over 4 and I become capacitive again. If I went from here less than lambda over 4, then that would be inductive. Right? So that's sort of the intuitive argument that one side should become inductive and one side should remain capacitive. Okay. Okay, now these are all in parallel because we've gotten rid of those transmission lines. So this can become, so this is nothing but have port and a parallel RLC network. Okay, so this is our radiation resistance, the total radiation resistance. This is, let's say, uh, patch inductance, and this is the patch capacitance. This is our port. Okay. All right. So at resonance, we know that the resistance that you see is purely real and it's equal to RR. And we want this RR to be equal to 50 ohms. Okay. And that's really what we want. All right. So if you know that it's kind of a parallel RLC, in this model at least, then we know what the impedance looks like for a parallel RLC. Right, so we can draw that next. So we have or as a function of frequency, if I'm looking at the magnitude of the impedance, then it looks something like this. That's not good. It's going to draw it freehand. Like that. Right? And we know that, okay, for a parallel RLC, at resonance, the impedance is purely real and it's equal to RR. Right? And then if I look at the angle, the impedance, or the phase of the impedance, then it goes from plus 90 down to minus 90. Okay. And we know that this is the case because, at very low frequencies, it's purely inductive. Capacitance becomes an open circuit, and very high frequencies, it's purely capacitive because the inductor becomes an open circuit. Right? And that's the parallel RLC model. We go from plus 90 to minus 90. Okay, this is really an approximation because if we go back to the patch and look at it, we know that at very low frequencies, this is nothing but a capacitor, right? So it should not be an inductor at very low frequencies. But what happens is that you really have an anti-resonance point at some point like that. So the phase will cross and then reach this and then do something like this. Okay. So this parallel RLC model is not a very broadband model. So it's really only valid over a range of frequencies. And that range is typically much more or more than the actual bandwidth of your patch. So it's a decent model. But it's just important to kind of keep that in mind. Okay. So some design equations which are kind of useful are that you want the length of the patch to be approximately lambda naught over 2 times square root of epsilon r. because most of the fields are really under the patch, so that's dominated by the material. Um, so here I should specify that this region, so the patch is kind of lying on a dielectric, and this dielectric has an epsilon r. So this whole thing is a dielectric, and that dielectric constant is epsilon r. And in reality, because some of the fields are in air as well, what I have found, at least in simulation, is that 0.95 times lambda naught divided by 2 epsilon r is a better approximation. Okay, and this factor lambda 0.95, it depends on W and H. So the thickness of the patch and the width of the patch, or thickness of the dielectric and the width of the patch. Okay, and W is approximately lambda over 2, 2 over epsilon r plus 1. Okay, so W does impact the resonance frequency a little bit, even though L is kind of what dominates it, because the wavelength, because the polarization is along L, right? So the wavelength depends on L. But what does W do? So W impacts the gain of the directivity rather. It impacts the bandwidth, and it also impacts F resonance. So the actual resonant frequency, but to lesser extent. Okay, and H is usually determined by what kind of substrate you have available usually. So if it's higher implies, so there's no analytical expression for this. So if it's higher, it implies that you can have more bandwidth. Okay, so if you have a thicker substrate, you can get much more bandwidth than a thin substrate for a patch within some limitation. Okay, so why do you have more bandwidth? I mean, the simplest reason is that you have more fringing field, right? If this patch is very close by, then the fields are very tightly confined and not much fringes, right? So intuitively, if you have a very thick substrate, then you have more fringing fields and more can radiate out. Okay, that's the intuitive reasoning. But you can't make it too high. Okay, so if you make it too high, then you can get substrate modes. The substrate modes we haven't seen yet, but we'll see later. So these are modes that propagate within the substrate. Okay, the substrate itself acts almost like a transmission line, and that's not good because then it's not being radiated out to air, right? It's just getting coupled to the nearest elements and then causes all kinds of problems. So you don't want that. So that's the reason we don't make it too high. Okay. Another reason is that if you have a feed line, let's say a microstrip line on the same side as the patch, we'll discuss feeds next. The microstrips, the transmission lines can become lossy because they also start radiating. Okay, and we'll see you'll have a microstrip line that feeds the patch. And if you make the thickness too large, then the fields under the microstrip line are not confined and then becomes a radiative line, which you don't want. Right, so there are some compromises in terms of height as well. Okay, so that's the simplest kind of rectangular microstrip patch antenna. Now we can start discussing some variations. Right, so the first, obviously the most practical thing is how do you feed it? So there are many feed options which have their own advantages and disadvantages. So the first one is using an SMA feed, or a coax feed, I should say, rather than SMA. Let's call it coaxial feed. So what does this look like? So you have your patch, down plane, maybe like that, down plane, maybe like that. Right? So what you do is you connect an SMA connector here, or a coax connector, which has a pin that goes and touches your patch. So in practice, how would you do this? You would make a hole in your patch with a kind of a drill, make a hole in the substrate as well, and take a via, sorry, not a via, uh, an SMA connector which has an extended pin like that. You put it through, then you can cut it off here and solder this on top. Okay, so that's kind of what is done in practice. So that gives you an SMA connector like this. And then you can connect your coax to this SMA connector on this side and make that. Okay, but that's the idea. So it's usually something like this. Okay. Okay. So what's the advantage of this? The advantage of this is that you can use a thick substrate, right? Because you're not relying on any microstrip lines that are on this thick substrate. So they don't have to be lossy or anything like that. You can just come, connect here and get very large bandwidths. Maybe 15% is possible or something like this. And it has good polarization ratio. Oh, sorry, it doesn't have good polarization ratio. That's the downside. So this is good, this is bad. So it has poor polarization performance or polarization ratio. The reason behind that is that if you look at this from above, right, you have your patch like that, and you have a feed here. Now the fields coming from the feed for a coaxial line are radially outward. Right? So you obviously these fields can excite this mode, right? But since they are radially outward, they can also to some extent excite even this mode, right? And usually that mode would resonate at a different frequency, but frequencies are not exactly completely confined, right? So you can have some of that tail of your bandwidth from this mode creeping into your actual mode of interest. Okay, so you can get a higher crossport because of that. Now, ideally, that should not happen because you're kind of feeding it at this line of symmetry, right? Which means that the current has to be divided this way. Whereas this mode has a current like this, right? So it cannot be excited by current which has both components. But there is still some amount of excitation of even this mode. And the crossport performance can be a little bit lower. There are ways to control that, but it's something to keep in mind. Okay. So what's the next kind of feed? So you can also use something called a via feed, which is similar to this. And you have a top patch. You have your pin coming out like that. And instead of that being a pin, that can be a via. Right? And then you have your microstrip line on the other side. So via your microstrip line. And this is nice because you don't need any coax or anything like that. This can be, you can have your electronics out here and then they come in here and it excites this patch like that. Right? But the downside is that you need to use a multi-layer PCB for this. Upside is that you can get high bandwidth, right? Because your microstrip, this dielectric can be thin and this dielectric can be thick. Right? So you're kind of using the best of both worlds. Your microstrip fields are very confined, but your patch fields are very loose. They're radiating out. Okay. Third option is called an inset feed. So let's say you only have two-layer PCB, two metal layers, and you want to feed the patch from the top side itself. So then what you can do is you can bring in the microstrip line and then feed it close to the center. So this should be kind of not a very good patch. That's better. Okay, so you bring in your microstrip line, 50 ohm line, and we said that, okay, the 50 ohm point is somewhere a little bit inside. So you just make a cut and then feed it over there. Okay, and of course you can tune these parameters in HFSS using optimization or sweeps to find what is the width of this, what's the length of this, right? And it's usually not very far away from that 50 ohm point where you put the port. Okay. So nice thing about this is that it's the same side, right? You have only 2-layer PCB. So 2 metal layers, I should say. But it's more narrow band, right? Because it's single layer. Because it's single layer, you have to have a thin substrate. Otherwise, the transmission lines are poor. Okay. This also generates slightly higher cross pole. So polarization ratio is a little bit lower because you don't have an exact patch anymore, right? You have kind of a distorted patch. So you don't have a pure mode that's just like this. So this can excite some of these modes as well. Okay. But it's convenient. So it's one way to do it. Another way to do it is using a quarter wave transformer feed. Okay, so a quarter wave transformer is you take your patch. Maybe I should make a proper rectangle. Right? And then I said that, okay, impedance here is infinity. Right? But that's not really true because if you put a small connector here, if I connect a line here, then some current can exist here as well. So the impedance is not infinity. It's quite high though. It can be quite high. Okay, so then what you can do is you connect a small piece of line. Then you connect your transmission line, 50 ohm line here. And so let's say this is 500 ohms at this point, which we'll call as Z in. And this is your Z naught. And you can use a quarter wave transformer, which is a well-known thing in transmission lines, with an impedance of square root of Z in Z naught. Right? And that'll match your 500 ohms to 50 ohms. Okay. So once again, this is a two metal layers, same as earlier. This is also narrow band, but it has slightly better polarization ratio. Because this is still a pure patch, right? Okay. Another option called an aperture coupled feed. Okay, so here what do you do? So the top metal layer is again your good old patch. Then you have a middle layer, which is a ground plane that has a small aperture in it. And then the bottom layer has a microstrip line that goes beyond this aperture and excites it. Okay, so from the side view, it looks something like this. Be a patch, small aperture in the ground plane. And you have a microstrip line that's, maybe I should draw it a bit closer. Microstrip line that excites that aperture. Okay, so designing this a little bit harder. There are many parameters that you need to control. How much is this, how much is it going beyond that? And that adds, some capacitance to this node, right? Because this is a small piece of line that's open circuited. Then this slot itself has some capacitance associated with it. And then capacitance or inductance depending on the size of the slot. And then you have your patch up here, right? So there's also the width of this, the width and height of this aperture, and its location as well, right? So it could be here, it could be here, compared to the patch, I mean. So you draw your patch first, then have the aperture that you need to control with respect to the patch, and then you need to control the length of this line with respect to the aperture. Right? So there are many parameters that you need to tune. But it's a little bit more band limited, I would say. And this is kind of question mark. It depends on how you design this and what the thickness of your layers are. Right? So you can actually get pretty decent bandwidth even out of this. But if you have a thin substrate, then it can give you lower bandwidth. Okay, the only advantage of this is that you don't use any vias. So if you have a process where vias are very expensive or you cannot make vias, then this might be worth trying. Right? And the reason it became popular at one point, it was easier to model analytically. We could model these aperture coupled structures earlier, called Bethe couplers, the Hans-Bethe. Okay, but they're not really that, because we have now computational tools to model them. We don't care too much about that. So I'm just mentioning it. In some cases, it's actually kind of useful to do. Okay. All right. So these are the different feed techniques. Of course, there are many more, but these are the more basic ones and more standard ones. Okay. So now we can go ahead and design circularly polarized patch. So if I want circular polarization, what do I need? Right? I need two components. I need one V pole, one H pole like that, and one V pole like that. And then they need to have a 90-degree phase shift, right? If they have 90-degree phase shift, if it's like this, then the polarization would be this way, right? Or if this was 0 and this was 90 degrees, then the polarization would be this way. And hopefully you've seen that if you have, a cosine and a sine that are orthogonal to each other, then that produces a rotating circle, a vector that rotates around in a circle, right? It's the same idea here. Okay, so how do you do that? So there are many ways to do it. So one way is you can use two ports. So I use a square patch. And I have two excitations. So one here and one here, right? And since it's the same size on both dimensions, both modes are at the same frequency. And you can either use, like, let's say we use a quarter wave transformer feeds, that, and then I have a microstrip line here, microstrip line here. And I bring these two lines and I can connect it to a hybrid coupler or a branch line coupler. Right? Branch line coupler. And that would produce my 0 and 90 degrees. Okay. Okay. Hopefully you've seen branch line couplers before, but you can do different, you can even, you don't even need a branch line coupler. You can just have an extra length of transmission line for this one and just use a power divider. That's another way to do it. Okay. So erase that. So essentially we can feed it this way. That's that this is 0 degrees and this is 90 degrees. Okay. So this is nice because you can get a fairly wide axial ratio bandwidth. Okay, because It only depends on what the bandwidth of your branch line coupler is, right? Because your axial ratio bandwidth can be as large as the actual impedance bandwidth of this patch, as long as your branch line coupler is also kind of broadband. And typically they are much more broadband than your patches. Okay? So keep in mind, this is a square patch. One more thing to mention here is that this current and this current are isolated, right? Because they are orthogonal to each other. So one current doesn't excite the other current. So this mode and this mode are kind of uncoupled or isolated modes. Okay, that's one way to do it. So this is the first way, and this is more broadband in terms of the axial ratio bandwidth, but you need two ports, you need a branch line coupler, so that takes up more area, and you may not always be able to do that, right? So what if you don't have the area? What if you want to just have a single patch that automatically is circularly polarized? You can use a concept called uh, mode splitting. Okay, so once again, I take patch. Let's say I use a rectangular patch, or just general patch, right? So we'll say, this is L and this is W. But now I feed the patch on the diagonal. Okay. So let's say I'm using a coax feed in this case, it's on the diagonal. So then I'm exciting both modes now, right? Because you really excite this current, which can be decomposed into the V current and the H current, right? Okay, now both currents are excited. Now, if I look at what's really going on here, is that this does not use mode splitting. So this is still isolated modes, right? Both modes are assuming, okay, this feed doesn't introduce any mutual coupling between these modes. They are independent, right? So I have frequency, I have my impedance. So now I have, two peaks that, and they correspond to two different polarizations. And if I look at the phase of the impedance, one of them is like this, the other one is like this. It is slightly offset. And the idea is that you can design this such that at this point, when the amplitude of both these modes is the same, the phase difference between them is 90 degrees. So we want this to be 90 degrees. Okay, and by separating these two lines, by increasing the separation between them, you can find it such that exactly at one point, when the amplitudes are equal, at this point, you have a phase shift of 90 degrees. And you can separate these two by controlling the length and width. So you can set a parameter, you can set the length to be some p plus delta, and the width to be p minus delta. And you sweep delta until you get a good axial ratio bandwidth. Until the axial ratio is 1 at some point. So of course, the axial ratio in this case, the axial ratio bandwidth is low because this is frequency dependent. It's only really one frequency where that happens. At other frequencies, it becomes elliptically polarized. But at least at one frequency for free, basically, you're getting circular polarization, right? Okay, so even in this case, the two modes are not coupled. Right? Okay, now we'll actually do the coupled modes. So coupled mode splitting. So this is another way of getting circular polarization. What's the idea here? Now, the idea here is that you take your patch, you use a square patch in this case. If this patch has some current, let's say in this mode, what I can do is I excite the other current by making a tiny slot in this patch, a diagonal slot like that. So what does this do? If I have a diagonal slot, the displacement current in the slot has to be this way, right? Which means that it excites the other polarization as well. So now I have two modes, and these modes, they interact with each other through the slot, right? They're coupled modes. And when you have coupled modes, so a good example of that, of mode splitting, is if I have two pendulums like that, and each of them have the same resonant frequency, let's say, and then I couple them through a beam. Okay, then this coupled mode system has two resonances now. So one is an in-phase resonance, right, where this one is going this way and this one is going this way. So they go kind of back and forth together like that. And the other mode is an out of phase resonance, right? An anti-phase resonance, where when this one is going this way, this one also goes this way. So they go back and forth symmetrically. Right? And intuitively, you know, I don't know how, but we all know this, that when they go together, the frequency is slightly higher than the original resonant frequency. And when they're going towards each other, the frequency is actually a little bit lower. It happens a little faster. Right? So this is called mode splitting. This is a very general thing. It's not only for these kind of resonators. You can take any two resonators, you couple them, their modes will split. The reason that that happens is because you can show mathematically that a couple mode system has two independent solutions, and you can show mathematically that the differential equation gives you two solutions which have this mode splitting behavior. Okay, but we're not going to do that here. Just going to use our intuition to think about how to design this. Okay. So essentially, since it's a square patch, both these modes without the slot should have the same frequency, similar to having these two resonators that are independent from each other. Once you add the slot, they get coupled. The length of the slot controls the coupling strength, right? So if the slot was very thin, then the coupling strength would be the coupling strength would be very low because they don't interact much. And if the slot is large, thick, then the coupling strength is higher. So for very weak coupling, you don't see this kind of mode splitting behavior, but there is a critical point after which you'll see that mode splitting happen. And then for very strong coupling, the splitting is larger. So they split more and more, and the coupling is more and more strong. Okay, so essentially you will see again this two mode behavior, and the phase of both the modes has the same kind of phenomena. And then you can use this separation at this point by controlling the coupling between them to make it circular polarized at one frequency. Okay, so that's one way. Of course, there are other ways to introduce mode splitting, not just with a slot. You can come up with your own ways, but one of the popular technique is to so you start with a square patch and then make cuts on the ends. And then you make these diagonal kind of chamfers, they're called, right, on the ends. And the same feed here. So even in this case, you can just feed it here. So you have a single feed with this nice behavior. So again, that also makes those two modes interact. Okay. It's actually a little bit easier to design these ones than it is to design this. Right? Because depending on the feed, here I've assumed that these modes don't couple, but in reality they do couple. because this feed structure is not some idealized feed structure, it has some metallic components associated with it, which means that this mode and this mode will start interacting a little bit, and then it becomes difficult to actually independently control their frequencies by controlling the lengths. So this is nothing but a weaker version of something that comes under couple mode splitting. Okay, so that's why in some sense it's a bit easier to design these than it is to design that. But in this case, it's pretty simple. You just make a square patch, you feed it, make these cuts or make the slot, and only have to control the size of the cuts and the size of the slot. Because you know it has to remain a square patch for the two fundamental modes to be at the same frequency. Whereas here you're trying to control this length, but that might not be enough because you have some weak coupling going on. So it doesn't behave so nicely. Okay, so keep in mind that this is a small slot, although I've run it kind of big. Usually it's kind of small because we don't want that slot itself to radiate. Okay, that slot, we don't even want it to resonate, which means we don't want it to radiate, right? We don't want it to resonate because that will introduce a third resonance. We'll look at what that does next, but in this scenario, we want that to be small. Okay. Okay, so those are the different techniques for those are the different techniques used in making circularly polarized patches. There are more. So we use square and rectangular patches. You don't have to do that. You can use a circular patch and make that resonate at two different frequencies and try those kind of things as well. If you make elliptical patches, you can make all kinds of shapes, right? But at some point we have to say, okay, we've covered the basics, and then you can go ahead and read the literature and come up with your own designs. So next we want to look at bandwidth enhancement. So earlier in the last lecture, we looked at Babinet's theorem, but that doesn't really apply to patch antennas because patch is not a planar antenna. Right? You have a ground plane underneath it. So we really want to develop broadband techniques for patches as well. So one idea is to use mode splitting with the same polarization. Right? So if you have two different polarizations, then you get circularly polarized. But we saw here that you can get kind of broader bandwidth than just a single element because of this mode splitting behavior. Right? So there are many techniques to do that, broadly, which are all broadly classified as these mode splitting techniques. So one is called parasitic patch, where you have a single patch like this that is driven, and you add another patch next to it. Like that. Okay, and that's not driven. So there is some coupling between these two from the fringing fields. So when you excite this, this also gets excited because of the fringing fields. And then because of their interaction, because of their same size, and you get some coupling between them. So it's like two coupled resonators where one of them is driven, and that can enhance your bandwidth. Okay. Now, of course, you can extend this and you can put another patch out here, put a patch here, put a patch here, and you can get many resonances. Not always easy to control, but you can get pretty large bandwidth. And you also have larger directivity. Both these patches are radiating now. Right, so your directivity is given by this aperture, which is larger. Actually, it's not exactly that because the ground planes are what radiate. So even then, it's still larger, right? It's like you have one slot here, one slot here, one slot here, and one slot here. So overall directivity is larger. Problem, of course, is that you need more area, right? So it's not scalable to arrays. at least not scalable to phased arrays, which we'll see later, because this is essentially considered a single element. So you don't have enough area to put another element next to it, because the element spacing is determined by lambda over 2, which we'll see. And also the coupling is fairly weak. They are placed next to each other like that. So at least if you place something out here, in fact, coupling can be a little bit stronger because the currents are this way. So they can excite this way. The fringing fields are mostly here. There's not much fringing field here. Still, the coupling, even with this kind of structure, is not that strong compared to what we'll see next, because most of the fields are still underneath the patch, right? But like I said, you can get multiple resonances, more patches or more parasitic elements. So you can get slightly more bandwidth. Another option is a stacked patch. Where you have your driven patch. This is the side view now. And you add another patch on top of it. This is actually kind of hard to design, I would say, because, how do you make, there's one patch with this ground plane, the other patch is this with ground plane. They have two different resonances, right? So to make them, to get the coupled mode behavior, you need them to have the same resonance. So you need to control the dimensions pretty carefully to get good behavior. Okay. But the nice thing about this is that it's lower area. But of course, you need multi-layer PCB. That can be more expensive, but you have very strong coupling, right? Because they are interacting they're interacting with each other with the fields that are underneath the patch. So you have very strong coupling, right? Most of the fields for this patch are confined here, and that's interacting with this one's fields, which are confined here in some sense, right? So you get pretty good coupling. Yeah, and of course, the directivity is a little bit lower, but that's fine compared to a typical patch. Okay. Third option is a use slot patch, which is my favorite in some sense. And I like them for several reasons. So what is it? So you have your regular patch, and you cut a slot in this patch. That's a U-shaped. So basically, this is all metal. You have a feed somewhere in the middle. Okay. The reason I like it is because it's almost for free. The same area, right? It's scalable to arrays. Single layer. Don't need any extra layers. And you also have good polarization performance. Or I should say decent polarization performance. Okay, it may not be good. So what does that mean? Because, field here, it's this way, comes out like this, and then comes out like this. This field and this field are opposite directions. So they cancel each other in the bore site along Z hat. But in reality, actually, the electric field goes to zero at this ends. So there's not much radiation from here anyways. Most of the radiation comes from this section. Okay, but even if there is some radiation from here along the Z direction, so along this direction, which is normal to the patch in the far field, this and this kind of cancel out. The field from those two cancel out. Okay. So most of these designs that I've discussed here, I've already done in HFSS. And we also discussed some of these details before in the 6.5 hour long video I made on antenna design. But I wanted to go through them again, just for completeness for this course, since we have been discussing antennas in this class. but you can go through that video and look at different designs that I've done here and see how do you actually design this in HFSS and how do you make them work in HFSS. Okay. Okay. So the next thing we want to look at, which is a kind of new topic which I haven't talked about before on this, on this YouTube channel at least, is miniaturization techniques. So we won't spend too much time on this. We'll talk about basically the broad ideas. It's a big topic, that's why this is not really a purely antennas class. So I want to do a limited discussion, but we'll cover the basics. Okay, so what's the big idea? So we saw earlier, we saw that briefly we looked at the fact that, okay, if I have a very small antenna, it's not a very good radiator. But then much later in the class, we'll see where that comes from. We'll derive the Chu-Harrington limit. But within that limit, you can still do a pretty good job, right? So you can, let's say you're really pressed for area. The limit is between the size of the antenna and the bandwidth, right? So if you're willing to compromise the bandwidth, you can actually get pretty small antennas, okay, and still radiate decently well. It's really the limit is between size, bandwidth, and efficiency, or bandwidth and efficiency for a given size. But if you're willing to sacrifice bandwidth, you can get decently radiating antennas, even at small sizes. Okay, so the first technique is using symmetry, or I should say exploiting symmetry. So we want to exploit different symmetries in order to miniaturize our element. So how do you do that? So we have a patch, go back to our patch again. It's a side view. And we said, okay, impedance is 0 here on this line. And somewhat symmetric with respect to that line, right? Because the impedance is 0 here, what I can do is I can simply short my patch here. So short circuit is a 0 impedance, so I'm forcing a short circuit there, right? So when I force the short circuit there, I can remove this side, one of the sides. Of course, you have to remove the side which doesn't have the feed, right? Okay, and then I can actually draw this a little bit to make it a bit thinner. So that's my shorting pin. And I have only patch on one side now. Okay, and of course, I still have my feed, which was coming in close to this end, right? Okay, and this is my coax. Okay, so from top, what does it look like? Looks like I had my, this was, the rest of the patch was end up out here, maybe. And then I put a shorting pin here. I've shorted that out. And this was my feed, right? Now in reality, of course, the shorting pin will add some inductance. So you have to still tune the structure. It's not, you can't just put a pin there or a short circuit there and then assume it all works well. And there are different ways to put a shorting pin. So you can put multiple vias. You can actually even put just a single via out here. Okay, and that's decent enough. So that will still make it resonate as long as you tune this well. Okay. So this antenna is called a PIFA, planar inverted F antenna. Okay, F because this looks kind of like an F, right? Where is the F? This is the F. is an inverted F. Okay, so these are very popular for phones and small uh, and PCBs and RFID tags, things like that. Okay, so although I've drawn this kind of structure from a PCB, you can also make the same antenna planar, right? So I can have exactly what I have here, right? But this is at a single metal layer. So I have, this is all a ground plane, this is all ground plane. I have a coaxial line coming in. This coaxial line bends this way, right? So that would then be a planar inverted F antenna, right? So that's what PFA actually is. So this is actually called an EFA, inverted F antenna. And you make it planar and that becomes a planar inverted F antenna. So if you just cut the patch, put a pin there, that's called EFA. And then if you make the whole thing planar, then it's called a PFA. Okay. So this is pretty small already, right? But we can do more. So what are the other techniques? So another technique is to load it with circuits. I should rather call it enforcing resonance. Enforcing resonance with circuits. Okay, so what does that mean? The simplest example is we can go back to a dipole, or a dipole like that, right? Okay, so we know that a dipole is below resonance is capacitive because it's like a capacitor essentially at low frequencies, and above resonance it's inductive, right? So if I want to, so let's say my resonant frequency, this is F, somewhere F naught here, right? Now I want to match it at a lower frequency, or not match it, I want it to resonate at a lower frequency. Let's say I want to resonate here, right? If I want this to resonate here and radiate out here, then I know that this is going to be capacitive at this frequency. So to force it to resonate, I can add an inductor here, right? So that's one way to do it. Another way is I just match to this frequency. So whatever impedance I see here, these terminals, I add a matching network here to match to that frequency, to the impedance of that frequency, right? So you can force it to resonate at a different frequency by just adding some matching network or some resonant element, right? Based on the circuit model. So that's the idea there. Yeah, another technique is using meandering lines. Meandering lines or space filling curves, which are sometimes called fractals. Technically speaking, it's not a fractal. There's a specific definition for fractals, but we'll be very loose here and say, okay, if it's a space filling curve, that's one example of a fractal. Okay. Okay, so what's the idea? Again, we can go back to just a simple dipole. Dipole is like that. Now what I can do is I can fold this dipole. Not exactly fold because there is something called folded dipole. I can meander the lines like that. And if you pay close attention to this, what's happening? So when I'm meandering something, I'll just zoom into one meander. Maybe we'll zoom into this section. Right? I have a current here that's like this. Use a different color. A current like this here, like this here, this here, like this. Right? So only these polarizations add up. These currents add up in the far field and these currents cancel. Right? Because these currents cancel, you still have a pretty decent polarization. Right? Still pretty linearly polarized. So you can simply meander a line and that'll give you a smaller area. Right? Another example is I can take my P far or E far rather. I had something like this, I had a feed, I had a pin or a grounding sheet here. Right? What I can do is I can convert this into pin like that, feed pin, grounding sheet, and I can make lines here. Because the polarization is this way, currents are flowing like this, I can break up that patch into just lines, thin lines that support the same current. Right? And then I can meander those lines. And so that's an example as well. You can do the same thing for PFA. And PFA looks something like this. Now I meander the line like that. Right? That would also work. Another example is a meandered slot. So I have my slot antenna, the microstrip feed, the coplanar feed. What I can do is, so I'm just going to draw the slot as a line. Okay. So that's the slot. And I had a microstrip feed like that, right? So what I can do is I can take this slot and I can meander it around. Okay. And then essentially you have a very long slot, which I have shortened out. The slot was supposed to be that long. Now it's taking smaller area. Right? And it's the same idea. You can get pretty good performance even at low frequencies from that. Okay. So there are a couple more broad ideas. I'll just mention them. So one is using a high K dielectric or high epsilon R dielectric. And we saw that that's the case, right? When we had the patch, it was lambda over 2 lambda over 2 square root of epsilon R. You can make epsilon R larger, and that will confine the fields more. So you can make the size of the physical size smaller. Or you can use engineered substrates, metamaterial substrates. Okay, I'm not going to discuss that right now, but essentially you can engineer the epsilon in such a way that you can miniaturize the wavelength inside it. Okay, and it's the same idea here, where you can use slow wave structures, slow wave antennas. Okay, so we know V equal to F lambda. Right, so if the velocity is somehow slowed down using an engineered material or an engineered structure, which are called slow wave structures, right? You can make lambda smaller, which means that the wavelength is smaller, so you can make the physical size small, right? And this uses essentially dispersion. We haven't really discussed them yet in the class, so I don't want to discuss these techniques now, but I'm just mentioning them for you to know that there are additional techniques as well. Okay, so with this, we'll probably close our discussion for today. Just to summarize, we started with the basic patch, discussed circuit models, dimensions, discussed different feed options and their advantages and disadvantages. We discussed how to make a circularly polarized patch. We looked at some bandwidth enhancement techniques, and finally, some miniaturization techniques. Okay, so this is more like a design lecture. We didn't do any mathematics really. So it's a little bit different than what we've done in the past. But as an engineer, it's good to have good intuition from the design perspective, but also be good at doing the analytical calculations and the derivations and the proofs, right? Okay, so it was a little bit long, but hopefully that was enjoyable. In the next lecture, we'll look at arrays, and then we'll move on to more advanced topics. If you have any questions, you can leave them in the comments. If not, I'll see you in the next one. Thank you.